So today I want to talk about searching and sorting, which are two problems that deal with arrays. So that'll give us an opportunity to, dwell on arrays and how to work with them, as well as going forward with the material. Searching and sorting. So searching means trying to find something in an array, and sorting means rearranging the elements in an array so that they're in some kind of order, increasing order or decreasing order. So there's a linear search. There's an example of linear search here. So in linear search, we might have an array that looks something like this. The values are not in order. And so what we need to do is look at each item. So if we're looking for something like an 11, then we look at the first item, which is a 3, it's not there. We look at the next item, 9, it's not there. And finally, we hit it at some point. The worst case is that we're looking for a value that's not in the array. That means we need to scan the entire array to determine that the value is not in there. So if we were looking for, say, the value 1 in this array, we would have to look at all 5 positions and compare the value at each of those positions with 1 and see that, the value in position 0 is not 1. The value in position 1 is not 1. The value in position 2 is not 1, and so on. Till we got to the end of the array, we never found a match, so we know, so 1 is not in the array. So that's searching. And this is a process called linear search. Then we have binary search. So look at this array. This is different than the other one. In this array, the values are in increasing order, or they could also be in decreasing order. What's important is that they're in some kind of an order. So now when we're looking for a value, we don't have to do it in a linear way. We can jump inside the middle of the array, look at the value in the middle, and decide the number we're looking for. Is it bigger than the middle element or less than the middle element? It's like searching through a book to find a page number in a book, right? You crack the book open in the middle. Is the number I'm looking for bigger or smaller than the value I'm looking at now? So, and you do what's called a binary search. You take a range of items, and you keep halving the range. You make the range smaller and smaller till you find the item that you want. That's called binary search. Here's the algorithm for binary search. So this is called searching. This is the topic of searching. There's 2 ways to search. Linear search, one item after another, or binary search. 2 ways of searching in arrays. There's other ways of searching through other types of organizations of data. So you can organize data in different ways. That's a topic which is called data structures. And we have a class on data structures specifically. Computer Science 330, CSE 330. And that's coming on later. So that's searching. And then there's sorting, which is having a list of values and putting them into order. So we'll look at that as well. So let's look at searching. So I have some kind of an array. So that's 7 elements. And what we want to do is say find a number. So we're going to find the position of, say, 13 in A. So we're looking at A, which has length len, and we're looking for, say, the number 13, and we get its position number should be 1. And let's look for all the numbers. Let's look for the value in position 34. That should be, the value 34 should be position 0, should be in position 0. So this function search, when we pass in the array A, its length, and the value to locate in the array, the function search returns the position of that value in the array. 34 is in position 0. 13 is in position 1. Minus 5 is in position 2, and so on. This is a complete set of tests we're developing here. I mean, this is kind of overkill, but that's what we're doing. And 0 is in position 6. What about if we're looking for 4? What position is 4 at in the array? Well, it's not in the array, right? 4 is not in the array. So what do we want to make? Let's have the function return something. What should we return? What do you think? What would you do in this case?
Return a string, you just said like not found.
Well, the string is, the thing is, the function has to return a data type. And it needs to return, search needs to return an integer position. So that we can't return a string. What do we return if we can't find a number in the array? What's a good choice? It has to be an integer. Some value that would indicate we didn't find K in A.
You do a negative number?
Yeah. Pick one.
-1.
Yeah. And that's exactly what's done in practice. See, you just did that process. That's what programmers of old did. They said, well, let's return a negative number. Well, which one? Well, I don't know. -1? And that's what stuck. That's how they did it. So, and that is the convention. I mean, you pick your language. You know, that's what you were going to get, -1. Okay? So if something is not in a list that has position starting at 0, the function will return -1 to indicate the value is not in the list. So we want to see that this returns -1 if we search for 4. Okay. So this is a stub. This is just always returning -1. So this should fail. And let's watch it fail. Oh, cert is not declared. See, this is the purpose of doing what I'm doing now. I'm making sure that the code builds with the stub before going any further. 34 is not in there. So we have to scan through A. We need to scan through A. So that means scanning through A means creating a loop that sets the values of an index variable, say I, to all the possible indices in A. So start at 0 and go all the way up to len. So if A of I is K, we found it. What do we return? What do we return? We're scanning through, we've got a loop here that starts with I equals 0, then goes to I equals 1, and I equals 2, like that. We're using this I to look at the value at that position in A. So A of I, that's the value at I. This is the syntax that means the value at I. The value at I is different than I. Here, I is 0, and the value at 0, the value at I, is 34. Here, I is 1. This position is 1. I is 1. And A of I, A of 1, is 13. So the value at 1 is 13. You see that? This has you gotta let that sink in. Now, in this loop, if we compare A of I to K and it's true, what do we return? I. Good. I know I'm reaching at least one of you. I don't know. It's hard to listen to me talk about it. I know it's so much better to, if you can express it yourself, you can sort of digest the material. That's why it's good to talk to people about this stuff. Explain it to each other, if you can. So here it is. That's the whole algorithm there. So we should pass all these tests. And we do. Although we didn't say all tests passed, did we? There we go. So that's a linear search. But what about if these items were in sorted order? Like if this was -5, 0, 12, 13, 34, 99, and 100. You know, it's the same values. We just put them in an order, so they're increasing. Now we don't have to look through the list in a linear way anymore. We can use binary search. So we're going to start with the middle. We're going to, look at the number in the middle and say, is that the number? No. Oh, well, is it to the left of the middle or is it to the right of the middle? If it's to the left of the middle, that means we've narrowed the range to here. So now that we have this smaller range, we're going to do it. We're going to perform this procedure recursively. So now we take of this range, we're going to take the middle, which is at 0. Or say, is the number we're looking for to the left of that 0 or to the right of the 0? Is it bigger than 0 or less than 0? Because it's in sorted order. And now, of course, for this array, which is small, it doesn't make any sense to use binary search. I mean, it's too small. You wouldn't want to use binary search on an array this size. But what if the array had 1 million integers in it? Well, then there's a difference. Binary search will complete almost instantly on the machine, but a linear search will take some time. So binary search is used for large numbers of values. All right, but because we're working on an example, we're just going to use, obviously an array of size 7 here. So these tests need to be fixed. Well, the test to look for 4 stays the same. Just like linear search, the value we pass in is not there, we'll return -1. So if we look for -5, -5 is now in position 0. 0 is in position 1. 4 is not in the list, so it needs to return, this function needs to return -1. 12 is in position 2, the third position. 13 is in 3, 34 is in 4, and so on. You might want to check for some of these other values, like what happens if this is very small, like a -44. And, look for numbers in between here, like this would be -4. Maybe right at the end. So I want to test the ends. I'm creating tests that are trying to find a bug. So I'm trying to stress the code here. So I want the boundary cases. It's the value just past the end. So there's our tests. So this should work. Let's test our test code with linear search. So the test, because we already debugged this linear search code, so we know that the tests are good. You got to pay attention to the tests. Now, if your test is wrong, you're going to search for a bug that's not there, right? So you've got to make sure the test is correct. All right, now let's change this algorithm so we have a more efficient binary search. Remember, with binary search, you've got a range of values. You've got a start index, which is initially set to 0, and an end index, which is set to the last index, length -1. So we've got a range from S to E. Initially, it's the entire array. All values. It's the index S, that's the start, and the index E, that's the end. So length -1, that's position 6, right there. That's the last position. And then once we have these, we calculate a midpoint from them. How do you calculate the middle index between S and E? What's the formula for calculating a middle index between S and E? Now, S doesn't necessarily have to be 0. It could be something else. Because remember the range, maybe here, let's suppose we looked at this midpoint here. And then we've narrowed it down to this range. Now the new midpoint is there, right? So that's where E would be 2 and S would be 0. So you can have different S's and E's. So how do you calculate the index that's right in the middle between S and E? What's the formula? Yeah, that's right. It's just the average. It's the average of S and E. Thank you. That's good. So it's S plus E divided by 2. Yeah.
Would you want us using that instead of the loop, or either one?
Yeah, we need to have that in the loop. That's right. So we're going to repeat this. Well, we'll have some condition here, okay? We're going to repeat this calculation here. So we're going to need a loop. We're just initializing S and E here to get started. That's the full range. That's the full array. And then inside the loop, we're going to, calculate the midpoint and then check, what's the number at A of M, right? That number is a number that we're looking for. What we're looking for, remember, is K. Is K inside A? Is K a value that's at some index, I, in A? So if K is less than A of M, right, what do? So here we're calculating M. That's the midpoint of S and E. So K, so we're going to look at, the value at M, at the midpoint. That's A square bracket M. That's the value at the midpoint. We're going to look at that number. If that number is bigger than K, like let's suppose, initially that's the midpoint right there. That's M is 3. And A of 3 is 13. So 13 is at the midpoint initially. It's the first midpoint we look at. Now, if we're looking for 10, if K is 10, then, 10 is less than the value at the midpoint, right? So it's to the left. So 10 must be in this range. And therefore, we can omit, all of that. We can toss it out. 10 can't be in there because the things are in order. So we're looking at 13, and we say, 10 is less than 13. There's the expression. 10 is less than 13, so we're going to adjust the range. The new range is going to look like this. Well, this range starts at, the start of this new range is 0. That's where the minus 5 is. And the new E, or end of the range, is 2. Oh, by the way, this endpoint of the new range is 1 less than the midpoint. So we leave S alone, but we adjust M. We adjust, E, so that it's 1 less than the midpoint. That's our new range. Oh, but what about the other case? That K is bigger than the value at the midpoint. Then what are we going to do?
S equals N plus 1.
Exactly. That's the range. S is now going to be 1 beyond the midpoint. So S equals M plus 1. Good. But we'll leave E alone. There's one more case. What is that one case? Huh? Yeah, it equals a K equals, that should be an if. It's right there. We found it. It's at M. What do we do?
Return N.
Exactly. Return M. Because the function returns the position of K in A. M, we found K at M, so we return M. It's good. Now, see, these three conditions are mutually exclusive and exhaustive. They cover all cases. So if K is not less than A of M and K is not greater than A of M. It must be the case that K equals A of M. It just has to be the case. So you can chop that and just do this. Because it has to be the case that K equals A of M. There's no other possibility at that point. Just a way to simplify. If you like to write it the other way, go ahead. It's not, I wouldn't say it's very costly, and if it improves readability, then go ahead and do that. So write it the other way if you like. Now the question is, when do we terminate the loop? What's the loop condition? Well, like S is getting bigger. Whenever we change S, we only make it bigger. And whenever we change E, we only make it smaller. So S and E are approaching each other. They're squeezing in. They're getting to specify a more narrow range at each iteration. So there's a limit to that process. So S needs to be less than or equal to E. If S equals E, is that a problem? Well, if we were looking for 10, we're going to hit a range that has one value in it, I think. And in that case, S and E will equal each other. So in the next step, we're going to calculate M. When S and E equal each other, we have one value in the range. We're going to calculate M. Well, M will just be the average of S and E, which is just whatever they are. And then we're going to check for that number. Did we hit it or not? And if it's not that number, then either going to increase S so it becomes bigger than E, or we're going to decrease E so it becomes less than S. So when that happens, the loop condition becomes false. This is the hardest part of the algorithm, is to understand this. The loop condition. See, if we're looking for 10, let's go through this. This is, so if we're looking for 10, S is going to be there in the beginning, M will be there, and E will be here, okay? That's the very beginning. So we're looking for 10. K equals 10. For K equals 10. So we look at the number at M. So K is less than A of M. So that means we're going to set E to here, which is 1, M minus 1. That's E is being set to M minus 1. I'm going to shave off this part of the range. Here's our new range. We're looking for K equals 10. So we calculate the new M. The new M is there in the middle. So we're going to look at the number at M. We're going to compare it to 10. Is 10 less than 0? No. Is 10 greater than 0? Yeah, 10 is greater than 0. That means we're going to bring S up. So S will be set to M plus 1. That means S and E are set to the same number, right? Because M is here, M plus 1 is where E is. So we're looking for 10. So S and E are on the same value. Now we compute M again. Well, M is right in there, right? So M is the average of S and E, so they're all the same number. Let's see what it is. It's 0, 1, 2. M, S, and E are all 2. They're all index 2. So is 10 less than 12? So we're going to compare 10 to A of M. Okay? Is 10 less than A of M? Yeah, 10 is less than A of M. And so we're going to bring E down. We're going to set E to M minus 1. So that means E is going to go to here. So now see the situation? Now S is bigger than E. See, we didn't, because 10 is not in there. So at some point, the positions of S and E are going to get into this situation where E is less than S. So that makes the loop condition false. We've gone far enough. When E is less than S, we've gone far enough. We've looked at everything. And after we've looked at everything, we didn't find what we were looking for, we return minus 1. That's what we do outside the loop. There's our code. And we even have test code already written, and we tested the test code with linear search. We know the test code is good. So let's use our good test code to test our binary search algorithm. It works. So that's binary search. And any questions on that? That basically covers this. We looked at linear search and binary search. I'll just quickly look at the, here are the problems. Implement linear search. Implement binary search. Basically, I presented the algorithm already. So it's kind of a memorization problem. But don't rely too much on memorization. Don't just memorize the symbols. You have to memorize the logic, the approach, the algorithm. And then the next exercise is sorting. So that's the next. But we looked at searching. I'm gonna